Hello guys, welcome to next chapter of Mycelium running. Let's get started. Chapter 3, Mushrooms in their natural habitat. Mushrooms can be placed in four basic categories: saprophytic, parasitic, mycorrhizal, and endophytic, depending upon how they nourish themselves. However, exceptions abound since some species employ more than one strategy, making them difficult to categorize. Approximately 8,000 macrofungi visible to the naked eye are saprophytic. Around 2,000 to 3,000 are mycorrhizal, and the remaining are either endophytic or parasitic. Although more species are constantly being discovered and categorized, the balance of populations can vary from drastically with environmental change. However, that deforestation causes a rise in saprophytic and a decline in mycorrhizal mushrooms. For example, now let's take a short tour through the four major categories of mushrooms. Saprophytic mushrooms, the decomposers. Saprophytic mushrooms, the decomposers, steer the course for proliferating biological communities, shaping and forming the first menus in the food web from dead plants, insects, and other animals. Most government and medicinal mushrooms are wood decomposers, the premier recycles on the planet, building soils in the primary outcome of the activity of these saprophytic fungi, whose filamentous mycelial networks weave in between the cell walls of plants. When organic matter falls from the canopy of trees and plants overhead onto the forest floor, the decomposers residing in the soil process this newly available food. Competition is intense. On the forest floor, a single habitat can actually the matrices of fungal networks sharing one space. These fungi secrete enzymes and acids that degrade large molecules of dead plants into simpler molecules, which fungi can assemble into building blocks such as polysaccharides for cell walls. From dead plants, fungi recycle carbon, hydrogen, nitrogen, phosphorus, and minerals into nutrients for living plants, insects, and other organisms sharing that habitat. This is this is the turkey tail. Turkey tail Chamax versicolor fruiting on a conifer dog deep in old growth forest in Olympic Park. The 29 is this is right. These towering old growth trees near Mount Rainier out of the out of thin soil but gather nutrients from afar from their mycelium rooted roots. In fact, most plants are supported by vast and complex colonies of fungi working in concert. Here I point to rich porous nobilism. For a closer view, see figure 50. A mushroom exclusive full growth habitat and the first fungus to be treated as an endangered species. Composers, saprophytic mushrooms can be separated into three key groups: primary, secondary, tertiary. Although some mushrooms species can cross over from one category to another depending upon circumstances, primarily second and tertiary decomposers can all coexist in one location. Primary and secondary decomposers such as oyster and meadow mushroom are the easiest to cultivate. Primary decomposers. These saprophytic are typically the first to grow on a twig, a blade of grass, a chip of wood, a log, a stump, or a dead insect or other animal. Primary decomposers are typically fast growing, sending out rapidly extending strands of mycelium that quickly attach to and decompose plant tissue. These woodland species include oyster mushrooms, shiitake mushroom, and maitake mushrooms. However, species employ different sets of enzymes to break down plant matter into varying stages of decomposition. Secondary decomposers. Secondary decomposers rely on the activity of primary fungi that initially, although partially, break down plant and animal tissue. Secondary decomposers all work in concert with anti antinomicides, other bacteria and fungi, including yeast in soil, in the forest floor, or in compost piles. Heat, water, carbon dioxide, ammonia, and other gases are emitted as byproducts of the composting process. Once the microorganisms, especially antinomicides in the compost piles, complete their life cycle, the temperature drops, encouraging a new wave of secondary decomposition. Cultivators exploit this sequence to grow the white button mushroom, the most widely cultivated mushroom in the world. Other secondary saprotropic that compete with compost grown mushrooms are inky caps, belonging to the family Coprinae, which includes the choice edible shaggy mane, Coprinus, and other, including the hallucinogenic Paniosella severant in outdoor wood chip beds. The ambiguous Strophyra industrial growers try to thwart these undesired invaders by heat steaming their compost temperatures inhospitable to their spores. Okay. Figure 30. David Aurora, author of Mushrooms Demystified and All That the Rain Promises and more, in position to take a photograph of a family of ambiguous sophrophores near my home. Figure 31. My daughter Lorena Stammet sits beside the garden giant, which is deep burgundy in color when young and fades as it matures, sometimes achieving a majestic stature. This mushroom can be both a primary and a secondary saprophyte, but is dependent upon soil microbes for food. Figure 32. Commercial button mushroom cultivation in Holland. This mushroom is a classic secondary saprophyte growing on compost, and this image is the honey mushroom from the stump. Secondary decomposers as a group seem more versatile than primary composers for dealing with complex assortments of microorganisms, since they have evolved in direct contact with microbially rich soils. Secondary decomposers typically grow from compost material, right? The best culinary Porphyria species, the garden giant or king Porphyria, is an example of an intermediary between primary and secondary decomposers, since this species first digests fresh debris and then continues to thrive as complex communities of microbes join with it to create soil. Now the tertiary decomposers. This difficult to categorize group includes fungi found toward the end of the decomposition process. They thrive in habitats created by primary and secondary decomposers over a period of years, often popping up from soils, holding little decomposable material. Tertiary decomposers include species of Canocybe, Agroscape, Mycena, Pluetis, and Agaricus. Tertiary decomposers rely upon highly complex microbial environments. The division between secondary and tertiary decomposers is often obscure. Mycologists simply call tertiary decomposers soil dwellers for lack of a better description. Some mushrooms initially act as parasites, and once they have killed their hosts, they act like saprophytes, growing on their dead remains. Honey mushrooms belonging to the genus Armillaria are good examples of species that grow both parasitically and saprophytically. Parasitic mushrooms, blights of the forest or agents for habitat restoration. Parasites are predators that endanger the host's health. In the past, foresters saw all parasitic fungi as hostile to the long-term health of forests. Although they do parasitize trees, they nourish other organisms. Parasitic fungi such as the honey mushroom, which can destroy thousands of acres of forest, are stigmatized as blights. However, most foresters are realizing that a rotting tree in the midst of a canopied forest is in fact more supportive of biodiversity than a living tree. Parasitic mushrooms may be nature's way of selecting the strongest plants and repairing damaged habitats. Ultimately, parasitic mushrooms set the stage for the revival of weakened habitats that are too stressed to thrive. Of all the parasitic blight mushrooms that are edible by humans, the assorted honey mushrooms such as Armillaria and Armillaria ostoi are the best known. One mycelial mat from a honey mushroom Armillaria made national headlines when a specimen was found in a Michigan forest that covered 37 acres, weighed at least 50 tons, and was estimated to be 1,500 years old. In Oregon, a far larger honey mushroom, mycelial mat, found on a mountain top, covers more than 2,400 acres and is possibly more than 2,200 years old. Each time Each time this fungus blight sweeps through, nurse locks are created, soil depth increases, and centimeters of soil accumulated to create ever richer habitats where once only barren rock stood. For further discussion of Armillaria, see page 47. Okay. So what makes mushroom mycelia different from the mycelia from mold fungi is that some mushroom species can grow into massive membranes thousands of acres in size, hundreds of tons in mass, and thousands of years old. Many saprophytic fungi can be weakly parasitic, especially if a host tree is dying from one causes, such as an environmental stress or parasitic infestation. Saprophytic that can take advantage of a dying tree are termed facultative parasites. For example, oyster mushrooms are classic saprophytes, although they are frequently found on dying cotton woods, oak, poplar, birch, maple, and elder trees. Although reishi is considered a true saprophyte by most mycologists, the Australian Quarantine Inspection Service has classified this medicinal species as a parasite and has banned its importation. Authorities on other islands, including New Zealand and Hawaii, also consider the mushroom a threat to their native trees. Some parasitic fungi behave like saprophytes, such as honey mushrooms, which may be found thriving on the corpse of their tree host. Most parasitic fungi, however, are microfungi, rarely visible to the naked eye, but en masse they inflict cankers and lessons on the shoots and leaves of trees. After their prominence in a middle-aged forest is symptomatic of other imbalances in the ecosystem, such as acid rain, groundwater pollution, and insect damage. After a tree dies, parasitic fungi may inhabit the tree, competing with saprophytes for dominance. Since the hosts for some parasites can be short-lived, natural selection sometimes favors fast growers. Forests have observed this with Phytophthora ramorum, the cause of sudden oak disease. This downy mildew pathogen can kill an ancient oak tree in days and an ancestral forest in a few weeks and remain viable on the dead carcasses of its victim, allowing a new staging platform for infection further into the mycorrhizal mushrooms, fungus, and plant partnership. Mycorrhizal mushrooms. Myco means mushrooms. Rhizal means related to roots. mushrooms which are related as mustake, bullets, and chanterelles form naturally beneficial relationships with pines and other plants. In fact, most plants from grasses to Douglas fir have mycorrhizal partners. The mycelia of fungal species form exterior threads around the roots of partner plants are termed ectomycorrhizal. The mycorrhizal fungi that invade the interior root cells of host plants are labeled endomycorrhizal, although currently the preferred term of this fungi is vascular mycorrhizal. Figure 34. Matsuki, which are mycorrhizal mushrooms known to mycologists as Trichalonoma agniver, growing deep in the old growth forest of Washington state. Both plant and mycorrhizal benefit from this association because ectomycorrhizal mycelium grows beyond the plant's roots. It brings distinct nutrients and moisture to the host plant, extending the absorption zone well beyond the root structure. The mycelium dramatically increases the plant's ingestion of nutrients, nitrogenous compounds, and essential elements phosphorus, copper, and zinc as it decomposes surrounding debris. David Perry 1994 postulates that the surface area, hence its absorption capability of mycorrhizal fungi, may be 10 to 100 times greater than the surface area of leaves forest. As a result, the growth of plant partners is accelerated. Plants with mycorrhizal fungal partners can also resist diseases far better than those without. Fungi benefit from the relationship because it gives them access to plant secreted sugars. Most hexols that the fungi convert to mantols, arbitols, and encroatols. One of the most exciting discoveries in the field of mycology is that microhaze can transport nutrients to trees of different species. One mushroom species can connect many acres of a forest in a continuous network of cells. In one experiment, researchers compared the flow of nutrients by the mycelium between three trees, a Douglas fir, pepper birch, and a western red cedar. The Douglas fir and pepper birch shared the same ectomycorrhizal, while the cedar had an endomycorrhizal. The researchers covered the Douglas fir to simulate deep shade, thus lowering the tree's ability to photosynthesize sugars. In response, the mycorrhizal channeled sugars tracked by radioactive carbon from the root zone of the birch up to the root zone of the fir. More than 9% of the net carbon compounds transferred to the fir originated from the birch roots, while the cedar received only a small fraction. Right, the amount of sugar transferred was directly proportional to the amount of shading. An earlier study by Sina Embrandt and others showed a similar bidirectional transfer of nitrogen-based nutrient elder to pine to a shared ectomycorrhizal mycelium. The book Mycorrhizal Symbiosis, second edition, Smith and his editor. 35. Dusty Yao happily holds harvest of wild porcines. The mycorrhizal polypterus are collected in the mountains above Telluride, Colorado. Jim Goen is pleased to find these delicious mustaches, a mycorrhizal mushroom in the mountains somewhere within. What do we have? Rika, my basket awaits a bountiful collection of these apricot smelling chanterelles, probably Chanterelles formosus. a mycorrhizal mushroom species growing in a 40-year-old Douglas fir forest near Olympia, Washington. My practice is to pick no more than 25% of the mushrooms of a wild patch, leaving young ones, and when encountering pairs of mushrooms, only pick one of them. Centrellas tend to form as twins, so cutting one mushroom near to the ground saves the other twin, allowing it to mature, formulate, sporulate, and spread. The cover of this excellent book, The Roots of a Young Pine Tree, are enveloped in the mycelium of the mushroom Solus bovianus. The mycelium extends the tree's range for absorbing nutrients and water while conferring a fungal defense against invasive diseases. This symbiotic pairing is the norm in nature, not the exception. The Simard experiment showed that a common mycelial net could unite three species of trees and underscored a remarkable ability of mycorrhizal fungi. Mycorrhiza can keep diverse species of trees in forests fed, particularly younger trees struggling for sunlight. Now we have a better understanding of how saplings survive in the shadows of elder trees that tower overhead and block out essential light. The fact that a single mycorrhizal mushroom nutritionally supported two different trees, one a conifer and the other deciduous, shows that the mycelium guards the forest's overall health, budgeting and multidirectionally allocating nutrients. Another example of a fungus and plant partnership is the Matsutake, which has a unique relationship with the non-chlorophyll producing candy stick plant. The candy stick gains virtually all its sugars from the Matsutake mycelium and the western hemlock, and or Sitka firs with which it associates. One mycologist I know speculates that the spot rooting of Matsutake on a slope of Oregon's Mount Hood may in fact be from a vast interconnected mycelial colony extending over thousands of acres. Further example is the big leaf maple, which projects vine-like aerial roots that ascend to the canopy of Pacific Northwest rainforests and are teamed with microhaze. Our understanding of the role of fungi in the forest is far more advanced than the simplistic views held just a few decades ago. Most ecologists now recognize that a forest's vitality is directly related to the presence, abundance, and variety of mycelial associations. A large portion of a large portion, one tenth to one fifth of the total biomass in the topsoil of a healthy Douglas fir forest in the Pacific Northwest may be made up of mycelium, and even more if we include the endomycorrhizal and ectomycorrhizae that thrive in the canopy. I doubt a forest can be defined without its growing mycorrhizal mushrooms has proved to be a greater challenge than first anticipated due to the complex interdependencies in which fungi play a critical role. Once the hurdle of establishing mycorrhizal mycelium has been overcome, decades may pass before a single mushroom forms. Nuances of climate, soil chemistry, and predominant microflora limit our success in cultivating mycorrhizal mushrooms in nature settings. The challenge we face is to tilt the balance so that a species of our choice can take up residence in such a complex natural setting, design habitats in which it can grow. Species native to a region are more likely than imported species to adapt readily to these designed habitats. Many American growers hope for huge profits when they try to grow European truffles, mycorrhizal mushrooms that sell at very high prices, in an attempt to duplicate the well-established truffle orchards in France, Spain, and Italy. where the renowned Perigord black truffle sugar fetches up to $500 per pound. Dozens and growers have tried to cultivate innovative non-native European truffles around the American, non-native European truffles around the American oaks or five filberts on their land, capitalizing on this dense desire. Several companies now market truffle inoculated trees for commercial use and calcareous high in calcium soils in Texas, Washington and Oregon have been suggested as ideal sites for these. One company, www.truffletree.com, that seems on top of its game, confirms that the tree inoculated with truffle mycorrhizae is absent of competitor fungi before shipment, although it makes no promises about yield. However, I know of only a few successes, one from North Carolina and one from North California, that have produced European truffles, and only after more than a decade of effort in the past 30 years, tissue culture techniques have increasingly replaced the tradition of transplanting truffle supporting trees. Despite this development, most plantings or inoculations of European truffles beyond their native habitat still fail to produce mushrooms, showing that growing native species is far more successful than growing non-native ones. A truffle chair in Washington recently produced the Oregon white truffle, tuber gibbosum, after patiently waiting for 20 years until the first truffles could be harvested. Nevertheless, commercialization of mycorrhizal gourmet mushrooms has seen little success outside of European truffle orchards, particularly those in France and Italy. The reality is, though, that our native species of mycorrhizal quickly outcompete the foreign European truffles. Since European truffles like basic high pH soil, the addition of calcium diminishes competition from native mushrooms. But this alone will not assure success. In New Zealand, where the repertoire of competing mycorrhizae is limited to just a few species, inoculated trees are likely to do better than in regions of North America that are resplendent with hundreds of competing mycorrhizal varieties. One method of One method of inoculating mycorrhizae calls for planting young seedlings near the root zones of Proven truffle trees. The new seedlings acquire mycorrhizae from a neighboring tree, and a second generation of tree carrying the mycorrhizal fungus is produced. After a few years, the new trees are dug up and replanted in new locations. This method has had the longest history of success in European sites where the soils, trees, and fungi are compatible. Another approach simple is Another approach, simple and elegant but not guaranteed, is to dip the exposed roots of seedlings into water enriched with the spore mass of a mycorrhizal candidates. First, mushrooms are gathered from the wild, and the spore-bearing surfaces are removed from the fruiting bodies, crushed and immersed in water. Thousands of spores are washed off, resulting in an enriched broth of inoculum, a spore mass slurry from a single mushroom. Floated a 5-gallon bucket of water can inoculate 100 or more seedlings. Microhized seedlings are healthier and grow faster than non-microhized ones. See figure 42. This one. Comparison of big leaf maples without and with larger micro. With microwaves, it's this one, and without microwaves, this. Okay. So we miss couple of images. Let's see. Big leaf maples grow in the rainforest of the Olympic Mountains in Washington State. Research by Cobb et al. Showed that this maple extends roots on its outer trunk that climb into the canopy, essentially creating a biosphere high above the forest floor. The biomass of these aerial roots is similar to the biomass of the subterranean roots. Upon these aerial roots, a complex habitat has evolved, including mosses and licorice forms, once thought to be parasitic to the tree but now known to be part of the tree. This one is the Perigord truffle, is one of the most sought after and highly regarded gourmet mushrooms in the world. This mushroom is mycorrhizal, growing in association with five filberts and oak trees. This one is the truffle burl, surrounds this filbert tree as the mycelium of tuber melanosporum consolidates its domain. The surrounding vegetation dies, creating a noticeable zone, and the calcareous soils are telltale sign that a telltale sign that truffle mycelium has taken root. Even if you're not successful in growing truffle mushrooms, the trees benefit from this pairing with the introduction of with the introduced mycelium. Tossing spores using water as a carrier on the ground above the root zones of likely tree candidates is another method that takes little time and effort. Habitats habitats should be selected on the basis of their parallels in the wild. For instance, chanterelles can be found in oak forests in the Midwest and in Douglas fir forests in the Northwest. Casting a spore mass of chanterelles into a forest similar to one where chanterelles naturally proliferate is obviously the best choice. However, the success rate is not high. Even tree roots confirmed to be microhazed with gourmet mycelia will not necessarily yield harvestable mushrooms. Fungi and their host trees may have beneficial associations for long periods of time with no edible fruiting bodies appearing. Inoculations of mycorrhizae by one generation of mycologists may not see fruition until the next generation. Chanterelles are one of the most popular collected mushrooms in the Pacific Northwest. Harvesting chanterelles is a controversial multi-million dollar business. Unfortunately, the gourmet mycorrhizal mushroom species are not readily cultured. Chanterelles demonstrate an unusual interdependence on soil yeast, making tissue culture difficult. At least four organisms must be cultured simultaneously: the host tree, the mushroom, Pseudomonas bacteria, and soil yeast, red soil yeast, needed for stimulating spore germination and healthy mycelial development. Not only do other microorganisms play essential roles, but the timing of their introduction is also critical to success in the fungal theater. Many experts believe that decades will pass before the plantations growing mycorrhizal species like Chanterelles mature to be a productive state. No one has yet grown chanterelles to the fruiting body stage under sterile laboratory conditions, although greenhouse grown pines have produced chanterelles after inoculation. In 1997, Eric Daniel, accompanied by F. Camacho, was the first to successfully cultivate a chanterelle fruiting mushrooms with a potted 16-month-old pine seedling in a greenhouse. Soon thereafter, Daniel patched this particularly vigorous strain which showed commercial potential. Field tests in 24 locations revealed Chanterella mycelium is the seedling's root zones 2 years after inoculation. Unfortunately, he could not stop grazing animals such as deer, squirrels, and beetles from foraging and disturbing his crops. More recently, Daniel started a Swedish company called Chanterellas AV to commercialize this breakthrough microtechnology in the creation of Chanterella orchards. His group has planted thousands of trees with the Chanterellas mycelium in an attempt to create mushroom plantations that produce mushrooms within a decade of planting. For the time being, only the patient might want to invest in mycorrhizal plantations. Given the long time involved in owning laboratory techniques. I favor the low-tech approach and traditional method of planting seedlings adjacent to known producers of chanterelles, mutsutake, truffles, and boletus, and then replacing the seedlings several years later. In this way, we can value the forest not for its quantity of harvestable lumber, but for its potential to harbor mushroom colonies. Mutualistic species fungal partnership. Mutualism occurs when two or more organisms work directly together for their mutual benefit, usually to prevent infestation by parasites and gather nutrients. Many organisms, from plants, ants, seek fungi as protectors and vice versa. This rapidly expanding field of study is one of the most exciting in mycology. Insects and mushrooms. Many insects use mushrooms as platforms for you know incubating and feeding their larvae. One of the first cases of mutualism to be noticed was the interrelationship between mushrooms and termites. The relationship, the mushroom journey, the mushroom genus Termitoceous includes several species of mushrooms associated with terrestrial termite colonies, especially in the tropics. Termites construct their nests with organic matter and cultivate mycelium. When abandoned, these mycelium-rich nests sprout delicious mushrooms. Termitoceous robustus, a delicious choice edible mushroom, sprouts from an aged abandoned termite colony. Since certain fungi function as natural bacteriicides and fungicides, some insects engage them as allies in an effort to counter infections from hostile bacteria and other fungi. Studies at Oregon State University show that atine ants, which include leaf cultures, which includes leaf cutters, grow Lepiota mycelium as a host for a benign bacterium that produces an antibiotic against struck, struck, struck is expressing itself in two forms, with one being an asexual mold. Figure 44. A disjoint mushroom Termitoceous sp is highly favored by the people of Central Africa as a delicious edible. The primordium began several feet underground, deep in a termite nest extending upward as long as a long taproot, and then forming a mushroom on the surface, especially when the nests are abandoned. How termites cultivate this mushroom has befuddled the best mycological minds in the world. So studies at Oregon State University show that atine ants, which includes leafcutters, grow Lepiola mycelium as a host for a benign bacterium that produces an antibiotic against destructive microfungal parasites. And they also feed Lepiota mycelium to their larvae. This complex partnering has allowed lineages of Artine ants to survive for more than 550 million years and to establish massive colonies numbering in the many millions of inhabitants. The mutualism between ants, mushrooms, and bacteria is a useful model for how we humans can live in closer harmony with our environment. Both ants and people benefit from the gardenership of mycelium by partnering with fungi. Many organisms, including humans, can resist these. Trevon Stemets excited to have his picture taken with the parasol mushroom, which is cultivated by ants to help them starve stay off, stay off infections. Many ants and termites farm fungi. Snails as fungus farmers. Snails and slugs love mushrooms. In unfortunate situations for many of us mushroom lovers, some snails enlist fungi to help them digest plants. Silliman and Neval found that a seaside snail that marsh periwinkle damages and then it feeders on certain grass where a particular fungus soon grows. Days later, the snails return to the grass, now overgrowing with fungus, and consume both fungus and plant. Grasses without the snail-enabled fungus grew 50% faster but were less appealing to feeding snails, whereas the plants covered with fungus were more plantable and nutritious for the snails. As you can see, the snail and fungus relationship affects other species in the marsh environment such as grasses. Endophytes, mutualistic symbionts. Endophytes are primarily benevolent, non-mycorrhizal fungi that partner with many plants, from grasses to trees. Their mycelia thread between cell walls but don't enter them, enhancing a plant's growth and ability to absorb nutrients while staving off parasites, infections, and predation from insects, other fungi, and herbivores. Generally, endophytes are not true saprophyte or parasites but are in a class of their own. In contrast to mycorrhizal fungi, many endophytes grow well under laboratory conditions, so we can make spawn by using methods like those used for saprophytic mushrooms. The vast majority of endophytes are undescribed and some appear to have lost the ability to produce spores, living vegetatively in a continuous mycelial mycelial state. Most endophytes described thus far as thus far are comicides. One example is Fascicula or Artica, a small cup-like mushroom that lives on healthy elder trees. Like many endophytes, this fungus is dimorphic, expressing itself in two forms, one being an asexual mold. Endophytic fungi are especially skilled at producing specialized mycotoxins, often alkaloids, a class of compounds that includes toxic cyclo- cyclopeptides and serotonin like tryptamines such as psilocybin. Endophytes hosted by grasses are similar to the ergot fungi whose alkaloids prevent their hosts from insects. Endophytes in large crabgrass, for example, appear to produce toxins that kill fire ants, and those in grasses such as the darnel weed cause sleepiness in cattle and horses, a fact long known to ranchers in Central America. However, Stanley Fair suggests that varying levels of alkaloids in plants may not yet afford consistent protection against herbivores. Because some grasses produce more mycotoxins than others in the same habitat, cattle may sometimes get a chemical cocktail, but other times not, making it more difficult for them to learn which grasses to avoid. Nevertheless, endophytes, which were once thought to be pathogens, are increasingly viewed as engaging the plant in a mutually beneficial relationship. In a 2003 experiment in Panama, researchers found that when endophyte free leaves from the chocolate producing cocoa tree were inoculated with endophytes, leaf necrosis and mortality declined threefold, suggesting a biodefensive effect is possible against other pathogens such as Phytophthora, the genus responsible for sudden oak death, a disease devastating California's native oak population. Spores from endophytes compete with many other free-flying fungal spores, According to one estimate, more than 10,000 spores of fungi land on each leaf per day. Amidst such competition, friendly fungi taking up precedence in is actually an asset to plants otherwise subject to pathogenic assault. Increasingly, mycologists believe that endophytic fungi may have co-evolved with hospitable plants. Wheat farmers benefit from the endophyte Performaphora indica. The basidomycete of this species has yet to be identified, so it's referred to as imperfect in the mycological world. This means that the fungus has no sexual phase, or the sexual phase has not yet been discovered. This species is a root-based endophyte that promotes the growth of wheat shoots and roots, and is capable of increasing leaf and seed population production by more than 30% while shielding roots from infection by pathogenic. Furthermore, seedlings paired with this mutualist successfully germinated 95% of the time compared to only 57% of seedlings without this species. Fruit and shoot mass also doubled. This species has also demonstrated growth enhancing properties when paired with maize and parsley. This fungus is easy to cultivate in the laboratory and widely coexist with many grasses. Clearly, pairing this and other endophytes with agricultural crops can increase yield, decrease disease, and reduce the need for fertilizers and insecticides. Endophytic fungi may have other practical applications in agriculture. Johan Hansen and other researchers feel filed a patent application using a Curvularia species isolated from grasses in the geothermal zones of Yellowstone and Lassen volcanic national parks. This fungus qualifies as an extremophile, a thermally tolerant species that grows at the far range of temperatures where life can be formed and confers some tolerance to drought and heat to the host plant. Hanson's research showed that grasses inoculated with this endophyte survived temporary exposed to extraordinary high temperature 158 degrees Fahrenheit or 70 degrees Celsius, while those without shriveled and died. Although wheat did not survive in their experiment, it did demonstrate increased drought resistance when watermelon seedlings and mustard seedlings were dusted with Curvularia spores. The spores germinated and inhabited the young plants. After the endophytic fungi became established on their hosts, researchers exposed the seedlings to extremely high temperature 122 degree Fahrenheit or 100 or 50 degrees Celsius. The seedlings with the endophytic spores survived prolonged exposures, but the same types of seedlings without endophytic spores died. The discovery of the Curvularia spores effects on plants may expand the biological tool set for myco restoration, possibly even drastically expanding oasis environments and encountering desertification. Figure 46. The tinder or amdow mushroom, a species found predominantly on birch, is distributed throughout the boreal forests of the world. Mycologist Jim Goen in Quebec, Canada with chaga, aerial Serotonium of Anotus obligus. Some woodconks, once seen as parasites on trees, may in fact be symbiotic endophytes. Worm and others report that the Basidiomycetus polypore forms Formitirus, the tinder polyphore or iceman mushroom can operate as a non-saprophytic endophyte in beech trees. This well-known polyphore This well-known polyphore is commonly found on beech, birch, polar, elder, maple, cherry, and hickory trees that thrive in the boreal regions of the world. In the Bohm experiment, healthy beech wood was cut into sections and incubated in cultured dishes for 8 weeks, whereupon fungal cultures of this conch emerged. A number of isolates of fomentarians were identified from the wood sections, and some proved to be genetically different strains. The fact that one species can perform separate but complementary functions in the forest suggests that the species may play a larger role in the forest than is presently understood. How many other perennial wood conchs do the same? I once received a call from a manager of a chestnut orchard in Quebec who told me that trees sporting chaga, this one, the aerial Cerotium of Inotus obliquus were resistant to chestnut blight. Cerotium is a compact mass of 100 mycelium with stored food that can sometimes become a detached entity. When he made a poultice of ground chaga and packed it into the lessons of infected chestnut trees, the wounds healed over and the tree recovered free of the blight. This leads me to wonder whether obliquus can operate as an endophyte as does forms Fomentarius, and whether these species or others like them could defend host trees against invading parasites. Many other mushrooms may be endophytes, including gill species. For decades, mycologists have been mystified how psilocybe cynaceans, a psilocybin mushroom, can suddenly appear when trees are chipped into landscape mulch. A mycologist friend of mine had a truckload of fresh, mostly elder chips delivered to his house in the spring. Soon thereafter, his mostly conservative friends took some home for mulching. That fall, most of their mulched beds were rooting with hundreds of potent psilocybes. Where could they where could they have come from? My mycologist friend wondered. The only plausible explanation is that the mycelia were already in the wood above ground while the trees were alive. Perhaps psilocybe mycelium can be endophytic but delays fruiting with mushrooms until the trees make ground contact. When engaging fungal allies, the mycorrhizal, saprophytic, and endophytic mushrooms, plants benefit in three ways. These complementary mycological systems help plants survive starvation, dehydration, and parasitization. The richer the fungus plant partnership, the more organisms that habitat can support. Masanobu, Masanobu Fukuoka, the former scientist, ecological visionary, and the author of the One Straw Revolution, understood that scientific reductionism failed to reflect biological synergies, processes that are still far beyond the most sagacious scientists today. He invented seed balls, clay soil, pellets rich in microbes and seeds designed to jumpstart weakened habitats. Although Fukuoka did not select the populations of fungi in his seed balls, he appreciated their contribution. One of our tasks is to better Fukuoka's pioneering method and customize it for myco-restoration projects, beginning with one straw. The saprophytes lead the charge, followed by mycorrhizas and endophytes. As caretakers for future generations, mushroom communities surrounding trees govern habitat progression. I believe fungi have evolved to support habitats over the long term, protecting generations hundreds of years into the future. Saprophytic mushrooms gobble up debris fallen from the trees and prevent invasion by parasites. The microalgae channel nutrients, expand root zones, and guard against parasites. Similarly, endophytic fungi, less well understood, chemically repel bacteria, insects, and other fungi. After hundreds of millions of years of evolution, fungal alliances have become part of nature's body politic. It's time for our species to partake in this ancient mycological wisdom. Figure F. Trella Vatica norm. Prof. Until recently, conventional wisdom held that gilt mushrooms did not exist underwater in 2005. This Tetrala, a new species, was discovered in the clear, flowing, pristine waters of the Rock River near Crater Lake, Oregon. This discovery opens up a new branch of aquatic mycology and raises many questions. How many other mushroom species grow underwater? So that's it, folks. That's the wrap up chapter 3, and tomorrow we're gonna be reading chapter 4. Thank you. I'll see you guys in the next chapter. Bye.